we present our work, Interactive Cartoonization with Controllable Perceptual Factors. Cartoonization is an image-to-image translation task that stylizes input images into cartoon styles. Although deep learning-based cartoonization methods show profound improvement in this task, they suffer a lack of usability when it comes to real environments. This is because the artists cannot intervene in the middle procedure of the model pipeline, as most of the deep methods take end-to-end inference manner. To improve its usability, we introduce Cartooner, an interactive cartoonization framework with controllable perceptual factors such as texture and colors. We show that the proposed Cartooner not only outperforms the other methods, but is also effective in various application scenarios. Cartoonization is a computer vision task that stylizes nature photos into cartoon styles. In this work, we mainly target cartoonizing the background scene so the user or the artist can more focus on the other important procedures in cartoon making, as this task can be utilized in many content creations, such as cartoon scene making. Diverse studies have been explored in this field. Particularly, deep learning-based methods show drastic stylization performance with an image-to-image translation formulation. Most of the methods utilize photo and cartoon image sets to train their network. In the traditional artist's workflow for creating a cartoon scene, we observed that there exist four distinct stages: sky synthesis, color stylization, texture stylization, and post-processing. Contrarily, previous deep learning methods opt to process the entire scene as a singular operation. This process disparity has created an inability for creators to intervene at any intermediate stage, thereby inhibiting a vital component of their artistic discretion. For instance, should an artist wish to modify the texture stylization aspect independently, current methodologies would prohibit such intervention. To address this gap, our work introduces a novel methodology, referred to as interactive cartoonization. This technique promotes usability and grants the artist greater control, specifically over the texture and color components, which are found to be the most frequently adjusted aspects within cartoon scenes. We develop a new interactive cartoonization framework, Cartooner, as shown in this figure. In the development of the Cartooner, two key control factors emerged from our pre-interviews, with creators as being of utmost importance: texture and color. For texture control, our aim is to facilitate manipulation of both abstraction and stroke thickness. In contrast to previous deep methods, which utilize a single encoder-decoder structure, Cartooner takes a decomposed approach. We have implemented separate decoders specifically for texture and color. This not only enhances the stability of the training process and improves overall performance, but also facilitates the independent control of these two key factors. To illustrate this, imagine a creator wanting to modify only the texture in a given scene. Cartooner allows for just this type of selective control, aligning more closely with the needs and preferences of the artist. In our preliminary analysis of texture, we found two key elements affecting it: the resolution of the target domain images, which impacts the stroke, and the receptive field of the network, which influences abstraction. Let's consider the resolution of the target domain images first. As the resolution increases, the network's relative receptive field decreases. Consequently, the network captures relatively thick strokes. Next, let's look at how the receptive field of the network affects abstraction. As the receptive field increases, the network captures a relatively larger area from the source image, which typically has high complexity. However, there is a loss when matching this with the high-resolution target image, which usually has low complexity. This discrepancy results in a decrease in complexity in the output image after training. From our analysis, it's clear that the receptive field and the resolution of the target image play crucial roles in texture control, impacting both stroke thickness and abstraction. The naive way to provide texture control would be to build and train different networks, each with a unique receptive field. However, this approach has inherent limitations. A single model under this system can handle only one texture level, and thus cannot manage continuous factor control. This inevitably restricts usability. To address these limitations, we propose the texture controller, a single model designed for continuous texture control. This solution enables a significant increase in flexibility and control over the texture, paving the way for more sophisticated and nuanced artistic creations. Each of these modules includes multi-branches, and each branch corresponds to different texture levels. This configuration provides comprehensive texture control by blending features from different branches. User input merges features across these branches, effectively defining the final texture level. During training, we jointly introduce multiple texture levels to enhance the flexibility and precision of texture control. Here are the loss functions to train the texture module in Cartooner. We use GAN loss and VGG-based content, and texture gram, and total variation losses, motivated by the style transfer literature. The color decoder receives both the encoder's feature and a color hint. It then generates an AB color prediction output. We've introduced an HSV augmentation to mimic color control, which is paired with a superpixel algorithm to reduce the complexity of the source image. By adjusting the HSV component, we create a color hint map. The color hint map is employed as a target color map when calculating loss, a crucial step in enhancing the controllability of color element. Here is the qualitative comparison with the state-of-the-art cartoonization methods, such as Cartoon GAN, Anime GAN, and Whitebox GAN. Cartooner shows great stylization quality, while also well maintaining the color of the original image. The quantitative comparison also demonstrates the Cartooner's great performance. We compare the methods with FID and clip-based FID, and the user's preference scores. Here are how our methods allow interactivity in cartoon scene making. Cartooner can receive reference images to control the color, as shown in the left figure. With the power of interactivity, Cartooner is highly useful when creating the background scene in cartoon making, as illustrated in the right figure. Here is an example UI of Cartooner. Thank you for watching. See you in CVPR.